We're going to see how we can use signal integration to determine the relative number of protons being represented by a given NMR signal. So far we've looked at how many sets of peaks should appear in a spectrum based on sets of equivalent protons, and then we talked about where they will appear. This is the chemical shift that's related to the shielding and deshielding effects. And so now we're going to look at the relative number of protons being represented by a given signal. We're going to use 1-bromo-2,2-dimethyl propane as our first example. And let's dissect this spectrum a little bit. So we know that we have two different types of protons here. And I'm going to start giving these alphabetical designations. And so usually we use lowercase letters. So I would say that the three that I've circled in blue, the three sets, I'm going to represent with lowercase a. And then the other two protons that are in a group by themselves, I'm going to call protons B. And hopefully we can agree that the protons labeled B are going to be the more deshielded because they're closer to the bromine. And so what we see here is we have two signals, of course. And this one here is corresponding to the 3 methyl groups. And this one here that's more deshielded is corresponding to the CH2 group. But what we need to talk about are the height of these peaks, really the area under the curve, the integration, a 1.6 to a 7.0. Now we know from looking at the structure that these protons here, the red protons that we call A, the signal should be representing 9 protons. And the signal that's coming from protons B should be representing 2 protons. So we would predict that we would see something like a 9:2 ratio in the integration. But sometimes when you get the NMR data back, the instrument may tell you, as you saw on the previous slide, something else. So say a 7:1.6. Really a 7:1.6 ratio is a 4.4:1 ratio, which is the same thing as a 9:2 ratio. When you report the numbers, say for when you're writing this up for lab or when you're doing this on an exam, you would use whole numbers, but sometimes you may get decimals out from the actual experiment, and then you need to convert that to the whole numbers. And you always have to take that into consideration when you are analyzing NMR data and looking at integration values, because if you had an unknown substance, for example, and you thought maybe it was either this compound or this compound, you see that the integration values actually could come out to look exactly the same. So you have a 6:2 ratio on the right, and you really do have a 3:1 ratio on the left, but the instrument may give you the data as a 3:1 ratio, or as you saw before, it could come out in some fraction of a number. And so you have to oftentimes use integration values with other pieces of data to make sure that it all makes sense. And in this particular case, you'd have to have something else to be able to tell these two molecules apart. Based on integration values alone, let's see if we can match up the spectra on the right to the structures on the left. I'm going to start with the structures and first of all group together equivalent protons. So the ones I'm circling in blue, I'm going to say as signal A for that compound, and I should see 3, 6, 9, 12 protons represented by that signal. The ones I'm circling in green, I'm going to call protons B, and that should represent 2. So I would expect to see a 12:2 ratio and just 2 signals for that compound. That happens to be this one down here. It's not a 12:2, but it's a 6:1, and that's the only one of these 3 that makes any sense. On the next structure, we have a group of protons here that are by themselves. I'm going to call that A. It should come out to be an integration of 3. We have 2 protons here that are unique. I'm going to call those B. and that's going to be represented, the signal should represent 2. And then we have these 3 methyl groups here. I'm going to call those C, and that should represent 9. So I would expect a 3 to 2 to 9 ratio, and I see that up here at the top. And so that spectrum goes with this structure. And this one goes with that structure. So by process of elimination, you can figure out that this spectrum must go down here, but let's go ahead and look at it to make sure everything makes sense. Let's start with equivalent protons. We have these 2 methyl groups that are equivalent, so I would expect to see a signal that represents 6. This proton here is by itself. That would be B, and it's going to be integrating to 1. And then we have a 2, oops, let me use a different color, a 2 and a 2, and a 3. And so I would expect to see a 6 to 1 to 2 to 2 to 3, and indeed we see that here.